Before I go on to vulnuses, I would like to actually touch up on the previous video, this diagram. Alright? And what this diagram says is that, if you still remember, is that any stresses acting over this particular criteria, this means that you're going to yield, right? But if your stresses acting within this particular boundary, I would say, alright, you are considered safe from yielding. Alright, we actually name this axis 1, 2, and 3. Correct. Now, any point that is dealing with the criteria can be called the so-called the unit vector E1 hat. Alright, so therefore this is E2 hat and E3 hat over here. Okay, so therefore if I were to write it out, it's like this. Alright, and therefore all of this equals to your yield stress. Alright, your particular point in remember this graph, your particular point is over here, and this yield stress at this point can be re-represented as the one shown over here. Alright, and this is the yield criterion. Alright, anything that goes above this yield stress means that you're gonna yield. In other words, anything that is outside of this boundary is gonna yield. Alright, so I'm just setting this equation. Okay, as we say, different materials has different yield criterion. Alright, maybe for steel, the yield criterion for steel may be this particular bigger thing. So anything that is within this bigger one is considered safe for steel. Alright, if it's bigger than this criterion, is you're gonna yield the steel. Alright, so different material has somewhat a larger one and a smaller one. Alright, but there will be a different shape, so that's why I just generalize everything in terms of this shape now. Okay, and if that's the case, then if the magnitude is 2, this is 1. Alright, because unit vector is 1, E1 hat, right? So if you were to express this in terms of a stress, it will be stress 1, because it's in the axis of 1. Likewise, if it's a stress 2, then it's this thing. Alright, so as you can see, the magnitude, so 2 times E1 hat is equals to your stress 1, so to speak, right? Because E1 hat and then plus times 2 is E2 hat. I mean E1 hat times 2, so it's 2 times E1 hat, which is equals to your sigma 1. Alright, so therefore what we can do is actually to just write simply, so this 2 itself, okay, I should have said that. I should have said 2 times E1 hat, this particular one is the stress itself. Okay, so sigma 1 times, so sigma 1 is 2, right? So 2 times E1 hat will give you a particular stress, and the magnitude of the stress is in fact just the stress itself. Alright, for example, if it's 2 times E1 hat, it gives you this magnitude. Alright, you call this sigma 1. Alright, and you can, so in other words, this can be equals to sigma 1, but I just want to show you that 2 is also equals to sigma 1, because E1 hat is simply times 1. Alright, if it's 2 times 1 is equals to 2. Right, 3 times 1 is equals to 3. Right, so E1 hat is always in the unit vector of 1. So at least you get a feel of it. So in such a case that happens, then what we can do is to simply re-represent your whole yield strength, alright, as maybe sigma 1 times E1 hat. If it's in the 2 direction, then you just simply sigma 2 times E2 hat and sigma 3 times E3 hat. Alright, and this sigma 1, sigma 2, sigma 3 is indeed your SY. As we say, that is the yield strength of a material. And in fact, this is in fact your hydrostatic stress, if you were to call it. Alright, and all along I just want to tell you that this is in fact the hydrostatic stress, because these are all stresses acting on the plane, alright, normal to the plane. If you have this plane, you have this plane, alright, and another plane that is going downwards. If you were to combine all this plane, you recreate whatever we have over here. Alright, if you were to draw whatever thing that you want, right, this shape over here, alright, and the stresses, as you can see, can be redrawn over here. Alright, so in fact the stresses, sigma 1, sigma 2 and sigma 3, right, are the stresses acting on perpendicular to the plane itself. Alright, but in a way that is slightly different. Alright, what we have seen is, although this is sigma 1, although we say that this is sigma 1, right, but it's acting on this plane. Alright, so therefore this is sigma 1, and sigma 2 is acting on this plane. Okay, so therefore we can just simply draw that sigma 2 is this plane over here, while sigma 3 is acting perpendicular to this plane, if you get what I mean. So therefore something like this. Maybe I should redraw that one. So this is somewhat the sigma 3. Okay, but however, normally when we represent things, we represent it in terms of the sigma 1, 2, 3. But in terms of 3D now, you are actually looking at in terms of the stresses acting on that particular plane. Alright, that's all. Okay, it is through experiment that all these normal stresses, or we call this the hydrostatic stresses, if you still remember in the previous videos. Hydrostatic stresses, you can simply watch this one, after which you can also watch this calculation, and you can get a feel of it. Alright, L2v7 and L2v4. Alright, you do also know that from that particular video, you still remember, the hydrostatic stress when you're acting on the cube itself, alright, is simply to change the volume of it. You can actually make it a smaller one or a bigger one if you were to enlarge it. Alright, but you can't deform it. Alright, the deformations is purely the deviatoric. So let's just deal with things and see how we can arrive something that we can use for the next video. So therefore this is the yield strength of the material in terms of the normal stresses. Alright, just a recap, this one is any stress tensor, alright, and then it represents all the three stuff over here. This is sigma 2, 2, this is maybe sigma 2, 1, this is sigma 2, 3, alright, things like that, if you still remember. And if you were to minus away the hydrostatic stress, which is simply in the domain of sigma 2, 2, sigma 1, 1, your normal stresses, you'll get something like this. Alright, as you can see the directions, alright, you actually removed your particular normal stresses. So this normal stresses that we have been saying all along is in fact your yield stress. Okay, and if you were to minus away your yield stress, what you have left over is the shear stresses of your yield stress to some extent. Alright, and therefore this as you can see, this leftover directions is gonna shear your piece. Somewhat is gonna shear. Alright, you're gonna deform your shape. And once we talk about deformations, we're gonna talk about plasticity. Alright, plasticity, talk about deformation. And this also is a proof to you that in the later parts we'll keep using this shearing KY concepts. Alright, and this shearing of the yield strength, alright, represented by three of the stresses, because they are all symmetry, right? So you can represent as sigma 1, 2, sigma 1, 3, and sigma 2, 3. Alright, but however we want just a value, so therefore normally when we write is square to find the average of them. Alright, or you can just simply write as a square root over here. Okay, so therefore sigma 1, 2 square plus sigma 1, 3 square is just simply so this shear stress of all this this shear stress of the yield strength, alright, is a value, is some number 5 whatever, is based on the equations over here, alright, that deals with your shear stress. That's what I want to say. And KY and SY all together will have some sort of a criteria stating that if you were to cross over that particular criteria, you may actually deform the shape. You may actually change the shape. Alright, so maybe something like this. If you have a large changes within itself, the shearing part. Alright, and then the normal stresses, or the hydrostatic stress, or the principal stress, or we call this the yield strength of the material, is to govern it from changing the shape. Alright, maybe the values over here may be slightly lower, and therefore it causes this particular this few values to increase, to spike. For example, if this is 2, 2 and 5, and these are all 10, 12 and 15, and then you can really see that 10, 12 and 15 is greatly larger than your normal stresses, and therefore this shear strength is somewhat dominant, and therefore it causes a huge load of plasticity deform. Right, so normally you want to balance, or normally normal stresses are higher than your shear stresses. If you were to take a look, alright, 9, 8, maybe this is 5, this is 2, and this is 3, things like that. Alright, so normal stresses are always higher than your shear stress for some reason, but if you were to remove your normal stresses or your yield strength, the leftover is going to deform your shape. That's what I want to say. Alright, although it doesn't sound like that. In the later part of the videos that deal with the ball misses, you're going to use the yield strength and your shear stress of your yield strength to do some things. Alright, and the yield strength is in terms of this equation, where sigma 1, alright, is in fact your 1/3. Alright, 1/3 sigma h. So sigma 1 is equals to your 1/3 sigma h. Well, sigma 2 is also somewhat your 1/3 sigma h, something like that. Alright, for more proportional stuff. But anyway, this is somewhat the criteria that we actually derived from in the previous video, and then we kind of talk about it and derive the yield strength, matrices, and the shear stress of the yield strength. And later on, you'll see how it is being applied. And I shall see you in the next video for the von Mises one.